So thank you for the very nice introduction. Hello, everyone. Welcome. Actually, fun fact, after I met with Luke a couple of years ago, I had plans to come to Australia and visit on vacation, but it was last spring and, pandemic. And so that didn't happen. Then, as I said, I had a kid. So now closest thing we can do to visiting Australia is this online. And also, yeah, sorry that it's so late for the usual standards of the seminar, but we had some scheduling problems with daylight savings. So Australia jumping forwards, Germany jumping back. So this is kind of the compromise where you don't have to stay over for dinner and I don't have to wake up at 4 or stay up at 4. As Luke said, the talk is going to be recorded anyway, so if you need to leave early, I will not be offended. I will assume you're going to the pub, not that you're bored. Or if you cannot attend at all, you can also catch up later. If you're here live, I encourage you to ask me questions. I think there is a solid question Q&A time later, but in case there's something urgent, you can also stop me. If you're not here live, or if you come up with questions later, this is my email address, but I will also provide it again later, so you don't need to jot it down now. Also, if you come up with questions after the talk and you want to chat, just shoot me an email. I'll do my best to reply quickly. So the next 40-ish minutes are going to be about Aeon. Aeon is a board game that we designed to communicate about the emergence of life to a non-scientific public. So I will talk a bit about the context in terms of science and of science communication that originated this game, how the game works, how the game itself works, might have also around. And as it's supposed to be a communication product, I will also say a few words about what we want to say with it. And depending on time, I would also like to give you some sneak peeks on other things we're doing in this project. But first, I work at the Deutsches Museum in Munich, which is apparently the largest science and technology museum in the world, at least by surface, and it's self-reported by the museum. Before the pandemic, it used to welcome about 1.5 million visitors a year, which I am sure everybody knows is about the population of Trinidad and Tobago. But most importantly for us, or for this talk, it's the outreach partner of the Collaborative Research Center 235 Emergence of Life, which I will henceforth refer to just as the CRC, because it's a terrible mouthful of a name. Some of you already know about the CRC, as Luke talked about. He and Martin van Kranendonk, and before them also Albert Fahrenbach, visited us in the before times when retreats used to be a thing. And they all gave very nice and inspiring presentations, which now give me terrible pressure to deliver this time. But most of you don't know about the CRC, so let me say a few words about it. It's a large research project funded by the Deutsche Forschungsgemeinschaft, which is traditionally a very long German compound word, which just means it's the German Research Council. It's quite a large group of people, large and varied, in many different people are from different backgrounds. The project comprises about 20 PIs, or not about exactly 20 PIs, and 30 PhD students, 30-ish. Now the number of PhD students is a bit more in flux, since there's people coming in, people, new PhDs starting, old PhDs finishing, and so on. And the peculiarity is that each of the research projects has combines two different disciplines. So each research question is assigned to two different PIs from two different disciplines and their relative PhD students. So, for example, we have Christina here. Christina, do you see my pointer? Yes. Okay. So we have Christina here is a volcanologist, and she studies volcanic ash and volcanic lightning and the synthesis of organic molecules in these settings. And then we have Thomas, a chemist who puts this volcanic ash in watery environments and studies the possibility of metabolic networks emerging from this chemical context. So that just to give you an example. So we have two people from very different disciplines that look at the same question. And on top of that, we have me with an additional outreach project. And my task is to coordinate and supervise the activities. I'm not supposed to like do most of the content. The content is supposed to come mostly from the scientists themselves, and in particular, the PhD students. So the PhD students are the driving force of this outreach project. And like you can see here, when we have our Philippe and our Juliette, who are here presenting the game at a recent fair in Munich. And the goal of the outreach project is not to like bridge a gap between scientists and public, but to reduce as much as possible the actual distance between the scientists doing the science and the public that wants to know about it. And also ideally bring more people into the discussion. So what happens is that the PhD students get first-hand experience in science communication, which is vital and is increasingly important in modern academia also. They also get supervision from me and from and feedback from more of the museum stuff. So other people that also have science communication training. And they also get established platform with very wide reaches. Remember the 1.5 million people visiting the museum, to present their work and their science to a public that's as large as possible. Now, we had many nice ideas in return, what we get from the communication side is the insider perspective of the scientist. So we can talk about science kind of in the first person. Scientists communicating directly are a very trusted source by the public normally. And the young PhD students are a very creative source of inspiration, and they provided a lot of nice inputs and ideas of what to do. Now, we had a lot of ideas of what to do with this communication project, with public talks, museum open days, and so on and so forth. Then there was, this project started in 2019, summer 2019. So you can see where this is going. Spring 2020 was a bit of a bummer from the public contact point of view. But what we managed to carry out, some online talks we could do, but mostly what we managed to carry out, even in lockdown, and what we managed to do even without being able to actually meet, was to keep developing and trying out this game. So how did we make Aeon? Well, our initial idea was to make a school activity, something for the kids that they could try and play with as a school activity to kind of experiment and play around with ideas about the emergence of life. So we started deciding what this game should look like. How much luck should be involved, or how much ability? Is it supposed to be a quiz? Is it a cooperative or competitive game? Do you have to learn things before you play in order to be able to play? Or do you have to learn things during the game to advance in the game? So is it supposed to be that the person that knows the most about the emergence of life wins? Or does it work differently? Then we had to think about what kind of science we want to, so what are the scientific contents that we want to communicate? And with these things in mind, we picked the game mechanics that we thought fitted best, both the science and kind of our goals. Then we started the usual test cycle where you draft rules, you test the game, you see that you need to change the rules, add or change things. But in the background, there was always the idea of what do these rules mean scientifically? So what are the scientific implications of what we're saying with these rules? And then based on that, we had to change some things because we realized that there were things missing or not quite right. Of course, there is a degree of approximation, but then we realized that what we were doing was definitely not suited for schools at the moment. It was too long and a bit too complicated. So we broke off a chunk of the project and go for a proper box in store, buy it game, fully complete, developed, and then adapt that to a simplified classroom activity. So then we went into the final production, hired an illustrator whose work you can see around my presentation here and there in the background, and also later in the tests. Wrote a background booklet where we explain the scientific background of all the elements of the game. So we give a brief, very brief idea of the science behind every element of the game. Went into manufacturing, which is hopefully going to be over soon. Crowdfunded a good chunk of the manufacturing, of the production costs, and do promotion. And I'm listing all the things that we've done for the end production because the students were involved in all of them. So not just the game design, but also the background booklet, the talking with the artist, the crowdfunding the game. So they had experience in a lot of different aspects, also practical things of doing this science communication and science communication product. So let's have a look at the game and travel back about 4 billion years to a much different Earth. Now I will describe a few things. So I said, let's travel back to a much younger Earth, but because we ended up setting the game on Earth, but none of the aspects that we're talking about are Earth specific. You will see that all the problems that you deal with in the game are general problems of the emergence of life. One could set the game, we could think of the games as set in a different planet, and it wouldn't really make much of a difference. Other than we're aiming for life that looks kind of like what we have. You will see what I mean. So in Aeon, players represent different environments where we think that life could have emerged. And during their turn, they build a reaction network using these triangular tiles that represent abstract chemical reactions with some direction of the reaction, some inputs represented by these colored borders. Blue is generically molecules where nitrogen is an important functional element. Orange is phosphorus is an important element, and black is carbon. So there's inputs, there's outputs. And by laying these tiles next to each other, we will build a reaction network. And then from this reaction network, you can obtain resources represented by wooden cubes. Well, we'll deal with now with virtual cubes, but the game has wooden cubes you trade back and forth with the game. And they represent different resources. So there's yellow energy, and then there's 3 types of basic biomolecules. We have the black fatty acids, the blue amino acids, and the orange nucleotides. And you use these resources that you collect, you invest them to develop 3 basic processes of life. You build the membrane, develop a metabolism, and a replication. Oh, no. So it's a competitive game, and the first player to get all 3 of these processes plus 3 resources of the 3 cubes of each resource wins the game. So in a way, every time we play, we're kind of running an experiment on where and how life could have emerged. And although at the end point is not really necessarily a life form, because we're very careful with saying we're like giving a definition of life and definitely not defining it as just these 3 things, but let's say it's close enough that we can end the game there without starting huge philosophical discussions. So let's try to have a quick look at the game. And for that, I need actually 2 volunteers to help me with the game. We have Peptide Luke.
I'm going by RNA these days.
RNA Luke, and Jeremy also, I see, raised his hand. Or was that?
Hi.
And
Hi, Karl.
hello. All right. So we have Luke and Jeremy. Very good. Let's see if do you see do you still see the presentation, or do you see the game?
I'm seeing the game.
We're seeing the game, yes.
Fantastic. Oh, that's great. So I will play the first player just to speed up a few things at the beginning. So as you can see, we join an already started game, so I can show a few things. There is already a bit of a network built, and I'm playing as an ice field, which is an atypical place to look for life, but it is an environment where there is work being done in the CRC, for example. What a coincidence. And the peculiarity of the ice fields that people are researching on is this freeze and thaw cycles, where ice melts and freezes again periodically, and that kind of counteracts diffusion. And we represent that by adding a special ability that every environment will have its own special ability, kind of reflecting the features of the environment. And here I can, like, if I had biomolecules, I could swap them with things that are being produced in the reactions. And I also have already an established metabolism, so that might help me to make my reactions more productive. The first thing I do in every turn is draw 4 tiles at random from a bag. And now here we have the, also it's going to be useful later for the volunteers. You will just need to tell me which letter tile you want. And I think all the places where tiles could conceivably go in this setting are numbered. So you just tell me the number you want to place them on. So I draw these 4 tiles and I pick 1 to put on the board. And there are only 3 constraints to that. One is that it has to be next to an existing tile. And then the other constraints are that I have to match the direction of the arrows with the neighbors and the color of the border. So basically inputs and outputs have to match with the neighboring tiles. And you can also see here all the different types of tiles, I think. So there's the normal kind of reactions that I presented earlier. Then we have these nice ones that are exothermic reactions that produce additional energy. There is sources represented with this kind of atom-like symbol that kind of provide the simple chemicals to the system. And at the very end of all these reaction chains, there's going to be product tiles like this one that take the simple chemicals and turn them into a resource cube or biomolecules and other resources. So I take this tile here and put it here in 1. So you see that this arrow that goes out of here flows into there and the border matches. So we're all happy. The other tiles go back in the bag. Now, the next thing I can do is run reactions. And to do that, I take energy from my reserve and put it on all the sources that I want to activate. For example, here and here. And this activates all the reactions downstream of that source. So for example, from here, I activate all these branches here and here and this one. So this reaction will be complete because all of the inputs are kind of fed. While on this side, I would feed this side, but this reaction is not going to help me because there's one side missing that I did not activate this turn. So this all to say that the reactions produce one amino acid, and from this exothermic reaction, an energy, which are produced. And now I can try to use my metabolism to, for example, transform that energy into a biomolecule. And to do that, I need to roll a dice that I have here. So you will have to trust me that what I say has been rolled is actually correct. And if I roll equal or higher than my free energy, I get the bonus from that metabolism, for example. So let's see. I rolled a 5. Great. So instead of my energy, I get a nucleotide because I decided to change it into a nucleotide. And that is my turn because I don't have enough. If I had 1 cube of each type, I could try to buy a further mechanism. If I had 3 energies, I could try to invest free energy to make it easier to to get the bonuses in the future. So we can try and move to player 2, which I think by speed should be Luke.
Mhm.
And we start by drawing your 4 tiles. Oh, you're playing as the hot springs, which I'm told.
I see. We're all playing as a different environment. I get it. Sorry.
Yeah. The hot springs, I'm told, can like overflow and flow into each other, and that creates, since they are very chemically different, that creates a can explore a wider chemical space, and we express that by saying that the hot springs can play 2 tiles each turn instead of 1. So you have your 4 tiles there. Only thing you need to worry about is they need to match the arrow direction and border colors.
And I can rotate them.
Yes.
See, it seems like, well, I think what was confusing me about us being different environments is we've got like the same layout as you had in the ice in your stuff. So it seems like, does that mean that I already have those established processes as well?
The processes, the only thing we have in common is the board. So the chemical network. The processes that are established are specific for the environment. So in this case, you have a replication actually started, and more apparently in the past, you've invested more energy in advancing your free energy. So you need only a 3, not a 4, as I did to get your bonuses.
What I meant was like on the board, you've got the energy placed for one of the reaction networks.
Mm-hmm.
I still have that in place even though you placed it.
The energy is there, but it doesn't count as activating the reactions anymore.
Okay.
It's the energy accumulates on the sources for reasons that are way too long to explain here.
Right.
So you will have to place, if you want to run reactions, you will have to place new energies around on the things that you want to use. There was a question though.
Oh, excuse me, Carol was asking if there was an app version.
No, I see that Jeremy has his hand raised. Is it from before, or is it?
I think that was from before.
Okay. That was from before.
Oh, okay. I just keep seeing the pop-up, and I didn't know if it was any question. But yeah.
Right. Well, how about if I take C and place it position 4, so the blue is against the blue is against the tile.
Yes.
Does that make sense?
Yeah. Sure.
Yeah. Perfect.
Like that. Do you want to
that's it.
play another tile? You have, as the hot springs, you have the faculty to play a further tile.
Yeah. Okay, so if we go D in position 5 as well.
Okay. All right. Very good.
Yeah.
And now you can invest, you may or may not invest any or all of your energy into running reactions.
Right. Well, it seems like I need a black tile to do either metabolism, or all 3 in fact. So,
yes, you need, no matter which one you activate, they all cost 1 cube of each type.
Yeah, but I don't have a black cube, so it seems like I can't run it. Okay. Well, I guess that would be the end of my turn. Right?
So you need to put, I should have numbered the sources. So you need to like put the resource cubes on the on the appropriate sources, and that gives you things. So,
Okay. So if I take that slightly above 11 and to the right.
Yep.
Yeah.
And
that one I put down with number 2 and 3.
that here?
Yep.
But
does that make sense?
Not really, because then you feed like half of this and half of this. What you would do to get one black is to put this there. So you get all that fed, and you get a energy and other energy from there, and a black cube there.
Okay.
And then if you want, you can spend one of each to activate to establish any of the mechanisms.
Okay, well, let's have a go at replication.
Oh, actually, yeah, you have replication active. Sorry.
Yeah.
And you can try to double your biomolecule, your fatty acid. You could make it into 2. You want to try? Yeah.
Yeah.
It's a 6.
Oh, well done.
Excellent.
That's the best thing I've achieved today.
And now you would have enough resources to establish a mechanisms if you want. So you would have to like spend 1 cube, like these 4 cubes, and you could activate any of these in principle.
Okay. Well, should I? I'll try and establish a membrane.
Cool. And you will see what the membrane does so that's the end of your turn.
Yeah.
And we move to player 3, who is the hydrothermal vent, and will be played by Jeremy. And the hydrothermal vent, what happens there typically is serpentinization, or that's mostly what people talk about in hydrothermal vents. And we represent that by having hydrothermal vents just getting more energy out of the reactions, because on top of whatever is happening, there is also more energy coming out of the serpentinization. So again, we draw the 4 tiles, and what do you want to do with? So you have to play 1. Jeremy.
Oh, this looks tricky. Oh boy.
Yeah, it took me a minute to understand what I was trying to achieve.
No, I mean, like the current network doesn't seem like there's a lot
I think besides so I don't think there's anything strategically
exactly
special at this juncture, and except for D, essentially anything could go somewhere. I mean, D could go to some not useful place, but everything could go somewhere.
I guess I'll place B at 7.
Yeah,
that seems to make the most sense.
Very good. And then the other tiles go away. And then you have membrane established already, and you can use your abundant energy to run reactions.
I guess I'll have 1 energy on the row with 6. So the one with the one on the right.
The one on the here.
That should give me 1.
They should give you 1 One nucleotide, yes.
Yep. And then I guess I'll have one on the left of number 6 on the same row, and then one
Here.
on the row with number 10. And then I'll
Okay.
get like a
So this
fatty acid.
this
and
produces so one energy from here. You get you produce from this reaction one energy from there, and one energy and one fatty acid from there.
Yep.
And then from here you get a nucleotide, and then you get a further energy just because you are the hydrothermal vents. So from all that is being produced, you get, so every player all the time, just never happened in this game before. Every player gets all the energy, and because there is diffusion, which is a big problem in Emergence of Life, as you probably are aware, you only get to keep one of the biomolecules you produced, unless you have a membrane, which again, by rolling the dice as before, allows you to keep more of these biomolecules in your reserve here. So Jeremy, you can now choose one of the biomolecules that you will keep for sure, and the other one you can try to keep with the membrane.
I'll keep the ribonucleotide to get the metabolism later.
Do you want to try to keep the?
Yes, please. Roll the dice.
It's a 5, so you also keep your fatty acid, and if I understood correctly, you want to also finally spend your resources to establish a metabolism. Great.
Beautiful.
Super. So this was like a round just to show how it works. And I'm running a bit late. So I'll quickly go back to, so what do we want to say with this game? So it's like, it's supposed to be outreach, right? So what are we doing? So the first thing that we want to communicate is all about chemistry, and it's all based on chemical reactions. That we also want to say that at some point during the development of life, you probably need to get life, something that looks like life as we know it. You probably need a membrane, a metabolism, and a replication. However, we make it very clear also in the booklet, this is not a definition of life, because defining life is a problem. Also, we want to show that first you need to get these complex biomolecules, and then the interaction between these biomolecules will give rise to the processes that underpin life. And last but definitely not least, we don't want to provide an answer of how it worked. It is extremely important for the communication of the CRC that there are different possibilities that of how it could have happened. So the abilities of the environments are in principle balanced. So there is no better environment, and you can activate, as you saw, you can activate the processes in any order you want. You don't have to go replication first. Usually what happens is that you develop processes depending on what the board looks like and what the abilities of your environments are. So some environments are more interested in, or are less interested in developing different processes because they can already kind of do it. But every time you play, you can get different solutions of the sequence and the environment where it happened. So for the communications aspect, it's also important who we're talking to and how. So our core audience, honestly, is probably people who play board games and or people who are interested in the topic and in this scientific topic. Luckily, there is quite an overlap between the two. And also, if we want to expand a bit further to what's the very core audience, I think, so we aim at like 12 years old and higher. We saw at like this, at this fair that I showed before, we saw that at 12 years old, they have zero problems dealing with the rules. They just quick explanation and they just go. Kids had a much easier time than their parents understanding the rules, to be honest. But we're adapting the game to be faster and with fewer rules in order to use it actually in schools, because right now it's hard to get through a game in less than an hour, I would say. So that's not going to work as a school activity. It's too long. Then Aeon is an example of active learning, which means you actively engage with the content instead of passively absorbing it as you would by watching a video, reading a text, listening to a podcast, which are all, don't get me wrong, absolutely great ways to communicate science. But it's just, this is different. It's not better necessarily, it's different. And also you don't have to learn with the game. If you want to learn by playing the game, there is stuff to be learned. And you will deal directly with problems like diffusion, pre-biotic synthesis, and managing resources and energy. But if you want to think of it as colored cubes and color tiles, there is no need to learn about the emergence of life. And finally, as I said, it's been made by scientists, so it's an example of direct scientist to public communication. Now, I will have to skip the sneak peek, I'm afraid, because yeah, I'm over time already. So, but the idea is that we're also doing a museum exhibition about this because it's a museum. So we have to kind of do an exhibition at some point, right? So that I will skip to the messages I would like you to take home, the very basic things, and that Aeon is a fully developed novel game. So we didn't just theme we didn't do an Emergence of Life themed Monopoly or something. We just developed a new game. And it's not a quiz that we dress up as a game. It's a proper game. It is a product, a science communication product, because playing with it, you actively engage with basic problems of the emergence of life. Again, as diffusion, what are the fundamental processes underpinning life, or the uncertainty of the answer. And every element of the game is rooted in science. So that's also an important aspect. And finally, that the game is embedded in a larger communication strategy with cohesive messages, and that features as direct as possible communication from the scientists to the public. With that, I would like to thank the DFG for funding all the work from me and the and the PhD students, and of course everyone at the CRC again, but particularly Joanna, Philippe, Christina, Bernard, Adriana, Juliette, Max, and Shri, who are the people in the actual development team. And of course, thank you for your attention.